Our subject today is the physics of the half-field Landau level nu equals 1/2. And our main tool is composite fermion theory. So before we get to composite fermion theory for the half-field Landau level, let us remind ourselves what we saw in the previous video about composite fermion theory. So we saw that the theory, at least at the mean field approximation level, gave us a way to map the problem of interacting electrons at density n and magnetic field B to interacting composite fermions at density n and magnetic field delta B. Delta B was smaller than B. That allowed us to map the fractional quantum Hall effect onto an integer quantum Hall effect. It gave us a simple and natural explanation to the existence of an energy gap at those fitting fractions at which an energy gap is actually observed. But the bad news was that it gave us a completely wrong energy scale, a kinetic energy scale, rather than the interaction scale that we know should be there. We also saw that if we go away from where fraction quantum Hall states are observed and approach fitting factors which are closer to nu equals 1/2, composite fermion theory explained the type of Shubnikov-de-Haas oscillations that were observed in experiments, and also the semi-classical motion of the electrons, of the composite fermions observed in the experiment, including the existence of a new length scale, the composite fermion cyclotron radius. Last, we saw that composite fermion theory gave us a tool, a calculational tool, to calculate the electronic observables, which are what we can measure in the lab, by calculating the composite fermion response functions, which are easier to calculate, to actually carry out calculations of, and converting composite fermion response functions to electronic response functions. Now, what we want to do now is to talk about the case where delta B is 0. So nu equals 1/2 and delta B equals 0. Maybe it's before doing that, let's present the experimental realization. Delta B equals 0 at nu equals 1/2. We know experimentally that there is no, at nu equals 1/2, there is no quantum Hall effect. No quantum Hall effect, no quantization of the Hall resistivity, no vanishing of longitudinal resistivity. In contrast, at nu equals 5/2, which you can view as two-field Landau levels plus a half-field one, we do see a quantum Hall state. And we'd like to understand both of these in terms of composite fermion theory, but not on the same day. Today we are going to talk only about this, and the next video we'll talk about this. So at nu equals 1/2, the composite fermions live at 0 magnetic field delta B. And we can ask, what do fermions do when you leave them alone with no magnetic field? Well, this is the prototypical example of a condensed matter system. This is condensed matter physics 101, right? Fermions at 0 magnetic field form a Fermi surface, and their interaction gives rise to a Fermi liquid. So first, let's ask ourselves, can we identify whether the nu equals 1/2 state carries a Fermi surface? How do you recognize a Fermi surface when you see one? There are two ways I'd like to mention. The first one is the cyclotron radius. That, of course, requires you to go slightly away from 0 field. And that is what we discussed in the previous video. The second one is what's known as the anomalous skin Hall effect. This is something that's measured at 0 field. And that demonstrates the existence of a Fermi surface, and that's something I'd like to discuss in some detail. So in fact, just to remind myself of how it is to teach on a board, I'll use this for writing. So what I'd like to think about is a system with no disorder, and we'd like to look at the response of the system at finite wave vector. And in fact, we'd like to look at the resistivity matrix at zero magnetic field, so B or delta B equals 0, so B equals 0, delta B equals 0. This would be for composite fermions, this would be for electrons. Fermions at zero field. What the resistivity matrix they have? Well, and we'd like to have it as a function of Q. Since there is no field, it will have no off-diagonal element. There is no Hall effect. But there will be two diagonal elements, and since we are talking about finite Q, the two directions, if I take Q to be parallel to the x direction, the two directions parallel to Q and perpendicular to Q are not going to be equivalent. And what I'd like to discuss is the resistivity at the direction perpendicular to Q, which is rho yy. So it's this element that I'd like to discuss. And the reason I'd like to discuss it is that eventually we will translate it into a measurable quantity at nu equals 1/2, which will demonstrate to us the existence of a Fermi surface. So what can I say about rho yy of some fermions at zero field? Well, the resistivity, from Duda's theory, we know that the resistivity, very generally in the presence of disorder and so on, is m over n e squared tau, where m is the mass, n is the density, e is the electron charge, of course, and tau is the relaxation time. And the relaxation time is something you can measure in your head as a thought experiment. It's not easy to do. By the following procedure, you prepare at time equals 0 a current carrying state, and then you let it evolve with no driving force, with no nothing force that forces the current to continue, and then you let it evolve and look at how long does it take for the current to decay. The relaxation time of the current, the decay time of the current is the tau you put in here. So I'm going to use this expression and wave my hands to get rho yy with no disorder this time, but with finite Q. So here's the x direction. And I'm going to prepare, I need the rho yy, so I'm going to prepare a current in the y direction that is oscillatory as a function of x. So it points upwards in one here, downwards here, upwards here, downwards here, and so on and so forth with some wavelength lambda or wave vector q. And I'm going to ask, that's what I'm going to prepare this current pattern at time equals 0, and I'm going to ask how long does it take it to decay. How do I prepare such a current? I need to take the Fermi surface at this point and shift it in momentum space slightly upward. So let me draw the Fermi surface here as a function of x. It's going to be shifted upwards at this point and shifted downwards at this point and shifted upwards at this point and shifted downwards at this point, and so on and so forth. Those are supposed to be Fermi circles, and they are not supposed to be shifted so much. It's, of course, exaggerated, but you remember how teaching on blackboards is. So this is the current we prepare at time equals 0. Now we let it evolve in time, and it will decay. Why will it decay? Because you see, this is a Fermi surface. There are here electrons that are moving this way. There are here electrons that are moving this way. Here there are electrons moving this way and this way. Yes, there are more electrons flowing up here than down, and more electrons flowing down here than up, and so on. But the effect that there's a whole distribution of fermions moving in all directions will lead to all this being mixed. And the time it will take for this mixing to occur, we can estimate pretty easily. The length scale, this length scale, is of the order of 1 over q. Forget factors of 2 and pi and all that. I'm not worrying about them. The velocity is of the order of v Fermi. So the relaxation time is just this distance divided by the velocity. It's 1 over qvf. And now if I go and substitute it here, I get rho yy, which is of the order of m over ne squared times q v Fermi. And write again rho yy being m over ne squared q vf. Now you see what's happening. mvf is the Fermi momentum, so it's h bar kf. N is kf squared, again, everything up to numerical factors. So this would go like h over e squared times q over kf. This equal sign should also be interpreted as going like. So ρyy, the resistivity of fermions at zero magnetic field, is linear in wave vector q. Goes like h over e squared q over kf. Now, we already said before that the longitudinal resistivity of the electrons and of the composite fermions are the same, because what differs between the two is the whole resistivity. So this is also the longitudinal. This is rho yy of the electrons at nu equals 1/2. But rho yy as a function of q is not easily measurable. What is much more measurable, not easily, it's not a simple experiment, but what is much more measurable is the conductivity at finite q. And that requires us to, in order to get the conductivity, we need to invert the resistivity. Let's now have some space on this part of the board and write that sigma xx is rho yy divided by the determinant of rho. And the determinant of rho is dominated by the whole resistivity that doesn't have any q dependence, leading to sigma xx being proportional to q over kf. So this linearity in q, which came out of the fact that we had a Fermi surface here, this linearity in q that came out of this mixing of the currents that comes out of the Fermi surface, this linearity in q translates all the way to the electronic sigma xx, which is measurable in experiment. Now, how do we measure it? Sigma xx is a measure of energy absorption. So what we do, as we already said in the previous video, we apply acoustic waves, surface acoustic waves, onto a two-dimensional electronic system at nu equals 1/2 or nu equals 1/4 for that matter, and measure what part of it is absorbed, or measure the change in the velocity of the acoustic wave. In both cases, we can extract sigma xx as a function of q. And you see from this experiment that sigma xx is linear in magnetic wave vector, is linear in wave vector at 1/2 exactly for delta b equals 0, and in fact also at 1/4. So what we see from this is the prediction of composite fermion theory for the for the longitudinal conductivity as a function of q at filling fractions which have nothing to do with the quantum Hall effect. There is no quantum Hall effect there. this prediction is pretty nicely confirmed by experiments. I should say by passing, I emphasize, and I'm going to emphasize it even more now, that mean field approximation gives us some answers which are plain wrong, like the energy scale for the energy gap. So how come it gives us such a good fitting to a measured quantity, to sigma xx as a function of q? I think that this comes out of the fact that the expression that we get is sigma xx being up to some number, some combination of pure numbers, being e squared over h q over kf. So the only system-dependent quantity that comes in here is kf. E squared and h, of course, are universal constants. It's only kf that comes in here. And kf is determined by the density, and the density we control. So no dynamical quantities like effective masses or velocities come into here. It's only wave vector relative to the Fermi momentum. And that's probably what makes this work so nicely. Now, from what works so nicely, maybe it's time to raise the question, what about the weaknesses of mean field approximation? Can we go beyond it? What have we neglected when we thought about mean field approximation? We neglected the interactions, which means, we took a Hartree approximation in which the density is just uniform and does not fluctuate. But in fact here, when a composite fermion is moving, it interacts with the fluctuations of the density because the fluctuations of the density are like a fluctuating magnetic field. So we have a fermion that's interacting with a fluctuating magnetic field. And that's not included in mean field approximation. Can we take it into account somehow? Well, maybe before discussing that, let's ask what is the answer we would like to get. Do we want to get that these interactions are not important, or do we want to find out that they are? Well, on one side, if the interactions are not important, that saves us a lot of calculational effort and a lot of work, and that's appealing. But we need to change the energy scale. We need to change the energy scale of the energy gap. So we need the interactions to have not only an important effect, but a fundamental effect. They need to change the scale. They are not supposed to be perturbative. And we know from thinking about Fermi liquids for many, many decades, we learned, learning the works of earlier generations or earlier decades, we learned that the most dangerous type of interactions are interactions in which there is a slow dynamics. The most extreme example is just interaction with impurities. When there's no dynamics at all, the impurities are frozen. And you know that interaction with impurities gives you relaxation time, momentum relaxation time, which does not vanish as you get close to the Fermi surface. Usually, we base our Fermi liquid theory on the assumption that the relaxation gets relaxation rate gets smaller and smaller as we approach the Fermi surface. So this is a fermion at some energy above the Fermi surface. This is the Fermi surface. And we believe by the Landau argument that Fermi liquid theory would hold if the relaxation rate vanishes quickly enough as we get close to the Fermi surface. When the dynamics is slow, this assumption becomes questionable. And here it is very slow. So before telling you why it's very slow, let's first see let's formulate the problem. So this is our Lagrangian. We have the composite fermions, that's the symplectic term. They have a kinetic term. And there are other terms which I'd like to comment on. First of all, you see the symplectic term has an interaction with A0, with a zero component of a gauge field. A0 appears here and appears here, which means, and it's always linear. So being linear, it just enforces a constraint. When we integrate it out, we'll get a constraint, and the constraint will be that del cross A is alpha times phi naught times the density. And that's the constraint, that's how we build this story. So this is what this and these terms do. And the last term, this is the neglected hero of mean field approximation. This is the interaction term. And you see that using this constraint that we talked about, this interaction term looks like a B squared, like a magnetic field squared term. We have del cross A at point R prime, del cross A at point R, and interaction between electrons. So this is the problem we would have liked to analyze in detail. Now, why do I say that there would be a very slow dynamics in this problem? The reason is simply electrons in a magnetic field plus a little bit of composite fermion physics, which I'll mention. So imagine that you have a system and you prepare some density lump, some lump of density somewhere in the system, and ask yourselves, what would be the relaxation dispersion of this density? Well, why would this density relax at all? This is, densities in matter, in compressible states always relax. This is sometimes known as the Maxwell relaxation mechanism. And the reason for that is, it's a density, so it creates an electric field, a radial electric field. The radial electric field creates a current. The part of the current that is that makes the density relax is the longitudinal current, JR. If the electric field is all radial, the part of the current that's linear, that's parallel to the electric field, which is the radial current, will lead to relaxation. That part goes like the longitudinal conductivity, sigma xx. So the relaxation rate would go like the electric field. The electric field is proportional to the gradient of the potential applied by this charge density. So we have the Fourier transform of that, and the fact that it's an electric field contributes one of these Q's. That doesn't matter so much. What matters is it's a product of sigma xx of the Fourier transform of the potential, and believe me, there's a factor of Q squared. Altogether, we know that and here's the piece of composite fermion physics that comes in, we know that sigma xx at nu equals 1/2 is linear in wave vector. So we know that this product of these two guys gives us Q cubed multiplied by the interaction. Now, electron-electron interaction in 2 dimensions is inversely proportional to Q. The Fourier transform goes like 1/Q. So for for Coulomb interaction, you'll get a Q squared here. For screened Coulomb interaction, you'll get even Q cubed. In any case, the relaxation dispersion is I omega going like Q to some high power. And that is a manifestation of slow dynamics. So it's this slow relaxation that will make the perturbative, or our calculation of corrections to mean field theory be non-trivial, be non-perturbative. We're not going to get into this calculation in full details. That would take too long. I will put references in the notes. But let me give you the flow. If we want to go beyond mean field approximation, the first thing we need to do within, the general formalism of Fermi liquid calculations, the first thing we need to calculate is the self-energy. Out of the self-energy would be a function of momentum and energy. Out of the self-energy, we could extract the effective mass. We could then turn on a little bit of delta B, a little bit of magnetic field, neglecting this order as we did all along here, putting the temperature to 0 as we put as we are doing here, and then we can ask what would be the energy gap for fractional quantum Hall states which are very close to nu equals 1/2. Fractional quantum Hall states for a very large value of p. So this would be filling factors of p over 2p plus 1. But we will ask about very large values of p. And we will ask about those because then we are very close to the Fermi liquid fixed point where delta B is 0. Now, is this of experimental relevance? Well, so, because we cannot, because of disorder and temperatures and so on, we cannot go to too high values of p. But it would be of theoretical interest. And now, if we carry out this calculation, what we see is because of the combination of the slow dynamics of the density fluctuations and the type of interaction that the composite fermion has with these fluctuations, what we see is the energy gap changes scale. It changes scale, and instead of being kinetic scale, it is now of interaction scale of E squared, the electron charge squared, divided by the magnetic length. Now, there are various prefactors that you see here. There would be a difference between filling factor 1/2 or 1/4. This is this value of alpha. But there's also, what's important is there's a dependence on p. And this dependence is 1 over alpha p plus 1 times log of alpha p plus 1. If the calculation was not singular, what the mean field approximation would have given you would be 1 over alpha p plus 1 without the log. This log is an indication of the singularity of the calculation coming out of the slow relaxation of charge densities, and enabling us, this singularity enables us to change the energy scale of the energy gap. This is a brief discussion of this, but we'll stop here and raise the next question, which would be a teaser for the next video, basically. We talked about nu equals 1/2 as being a Fermi liquid of composite fermions leaving at delta B equals 0. Now, fermions at 0 magnetic field can form other states of matter too, right? They can form a Fermi liquid, but that's not the only phase they can form. So maybe we should also consider other possible phases, maybe incompressible, maybe compressible, that composite fermions may form at the half-field Landau level. We will do that next time.